team, it's your chemistry coach coming back here with video number 12. Hopefully our last one in this equilibrium series. For my class, this is chapter 15. So after this, you can do your chapter 15 part 1 and part 2 homeworks and then let me know you did them, right? Because we're doing them at home. Doing this online remote teaching is pretty crazy. Like I said, the bad part about this, I'm not with you guys. I have so much fun yucking it up with you guys, especially in lab. So it's really hard to lecture to my own face on my laptop rather than goofing around with you guys and picking on you and having you pick on me. I miss that interaction, that magic in the lecture hall. But I do have my favorite kitty cats here. I got my favorite beverages here, my favorite soda pops. Life is pretty good doing it this way too. So goods and bads and everything, mostly good if you look at it that way. What are we going to do for our last thing? No math this time. Yay, we're done with math. We are going to do a very, very popular, common topic called Le Chatelier's principle. I don't speak French, so Le Chatelier, I don't know, right? I don't know how to speak French, so that's the best I'm going to do. Le Chatelier. All right, what's this principle say? Once you get the basics of this principle, you can apply it to a lot of different things and it will make a lot of sense, but you have to, don't try to memorize stuff. Try to think about, again, chemistry is about patterns and processes. So you'll see a whole bunch of different definitions of this, but just in essence, let's say you've got an equilibrium system, right? It's a dynamic equilibrium. The forward rate, the reverse rate they're equal to each other. So the concentrations of all species are constant, right, at equilibrium. But what if we disrupt that equilibrium? Oh no, we cause a change, a disturbance, a disruption, whatever, yeah, perturbance, whatever word you want to use for that, and we push that system out of equilibrium, right? Remember, the equilibrium is the happy state. When we push it out of equilibrium, that equilibrium system goes, hey, man, I was happy where I was. You know, I want to go back to where I was because I'm no longer there because you pushed me out of it. However we did that, right? We'll talk about the different ways we can push a system out of equilibrium. But that equilibrium system is going to respond to that disturbance, right? And it's going to respond to counteract that disturbance, right? So if I push the equilibrium system this way, it's going to want to shift back to where it was originally. So any system, a dynamic equilibrium system that's been disrupted, will shift in response to that disruption or disturbance by counteracting it, right? It's going to try to counteract it. And there's three things we're going to look at for how we can disturb or disrupt a system in dynamic equilibrium. One, probably the most common, is altering concentrations. Two, altering the volume of the system, which therein affects the partial pressures of species, which we can think of like a concentration change almost. And then three, alter the temperature. So if you need to take a few minutes to pause this and review exothermic and endothermic processes, that would be very, very helpful because we're going to be using those terms from your introduction to thermochemistry before. We'll take a look at each of these in turn, but they all kind of overlap and interrelate. And what's good about Le Chatelier's principle, we can use this to cause or force a reaction out of equilibrium. Say I want to make more products. I can do some kind of disruption. I can alter the experimental or laboratory conditions of the system in dynamic equilibrium and force it to go right to produce more products, right? So maybe I'm running a business or something. I want to produce more so I can sell more. Boom, you can do it that way. Maybe I want to purposely shift it to produce less products and more reactants. I can shift it to the left by understanding the effects of temperature changes, volume changes, and concentration changes. So let's look at the first one, the concentration changes. I think that's the easiest. All right. Three types of disturbances we can do. Let's get rid of the neighbor's yard work here. All right. You got to love working at home. You got all this fun stuff going on. So we got three types of disturbances, right? Changing the concentration, changing the volume, which affects partial pressures, and changing the temperature. So we're going to look at concentration changes. So let's just think about, remember, think like you're the system. And you're in equilibrium, and you want to stay at equilibrium. So if somebody pushes you away from equilibrium, you want to get back to it. So what do you got to do to get back to where you were, your happy place? So in general, and really only needed to write the first part, the second part is just vice versa, right? if the concentration of any species, now here's a little, subclause, and that species has to be in the equilibrium expression. Remember, solids and liquids don't count. It has to be a gas phase or aqueous phase species. So anything that shows up in the equilibrium expression, you can get caught on a test on that one. If I change the concentration of a solid, it's not going to affect it. If I take the concentration of any species in the equilibrium and it's decreased, right? However I do that, maybe I add a chemical to something and it reacts with one of those species and brings it down. Maybe I purposely, suck a gas out of the product side. Whatever you got to do experimentally to decrease the concentration of any one of those species. However it's done, doesn't matter. The net effect is the concentration of one of the species has decreased in the equilibrium system. Well, that system's going to shift to counteract that. So it's going to shift either right or left. It's unique to each equilibrium reaction or equilibrium equation. So it's not always left or always right. It depends. It will always shift towards that species to try to bring its concentration back up. So if the disturbance brings something down, it's going to shift to bring it back up. So it's going to shift towards it to bring its concentration back up in response. Right? That's Le Chatelier's principle. And vice versa, if the concentration of any species in the equilibrium expression is increased, however we do that, then the system will shift away from the species. So if I increase the concentration of something, it's going to shift away from it to bring it back down to counteract that disturbance, right? So let's do an example. All right, gang, here's a typical quiz or exam problem you might see. Problem number 1, parts A, B, C, right? So here's an equilibrium system. In this case, we have a weak base, methylamine, ionizing in water to create the methylammonium ion and OH minus. Oops. Yep, that's correct. So let's take a look at 3 different types of disturbances that affect concentrations. And again, anything on the water is not going to have an effect. That's not in the equilibrium system. It's a condensed phase. But if I change the concentration of anything that's in the aqueous phase here, that's going to cause this equilibrium system to shift to counteract it. So let's say we decrease, however it's done, the concentration of the hydroxide ion over here. Right? We could do that by taking it out directly. We could do that by adding maybe an acid to it. Maybe we could add a strong acid like hydrochloric acid that would decrease the OH minus. However that happens, it doesn't matter. But what the system sees is this goes down, right? That went down. So the system goes, red alert, we are no longer in equilibrium. Our OH minus has been decreased, so we want to reform it. So to reform it, it's got to shift towards it, right? Anytime you decrease the concentration, it shifts towards it. So this is going to shift. You could either say to the right or towards products. Those are both correct answers. Okay? It's going to shift in response to that. Let's take a look at B. Let's say we increase the concentration of the methylamine over here on the reactant side. So this will change now. If we increase the amount of that reactant, red alert, we're no longer in equilibrium. We got to get rid of it. We've got too much of this reactant, so we need to shift away from it to bring it back down. So this is going to shift also to the right, right? Things to think about if you're, working for some chemical manufacturing plant or whatever, and you want to shift a reaction to the right to produce more products, right? So if we increase the reactant in this case, it's going to shift away from it towards the products to bring this down. In the process, that will increase more products, right? Now, last and not least, let's add a little twist to it. Let's say we add some 0.1 molar sodium hydroxide. The concentration is irrelevant in this problem. We add some sodium hydroxide. So we have to look at, well, what does sodium hydroxide solutions contain? This is a strong electrolyte. So in solution, sodium hydroxide breaks up into the sodium ion and the hydroxide ion. Right? So let's take a look at our equilibrium system. There's no sodium ion in there, so that would have no effect on it whatsoever. But it does have hydroxide ion. You see that? So I'm adding a solution that contains an ion that's in the equilibrium system, which means the OH minus, the hydroxide, is going to increase in this case. Boom. So I have successfully increased the concentration of the hydroxide ion, which means red alert, too much hydroxide, shift away from it. Because that was a product, it's going to shift to the left to bring that back down. So this would shift to the left to counteract the addition of the sodium hydroxide, which is the disturbance. So concentrations are pretty easy to do. Let's take a look at a little bit more challenging thing, changes in volumes and pressures. Hi guys. All right. So changing concentrations is pretty easy to think about. Changing volume and pressures, I think, is a little bit trickier to think about, right? We're looking at, you could almost think of partial pressures as concentrations, right? That kind of stuff. But if we're going to affect the volume of the container, it affects all of the gas phase species partial pressures at the same time. So you can't look at one individually like we could in part A or part 1 looking concentration changes. We have to look at the system as a whole. All right. So if we change the volume of the system, remember Boyle's law, if you increase the volume of the system, right, that's going to decrease the partial pressures of all species, right? Increasing the volume goes up, pressure goes down, right? We got more volume, so the gas particles get spread out, the partial pressure decreases. And again, pressure is the collision of a gas particle. Remember kinetic molecular theory. Gas particle collides with the surface of the container, and that creates pressure. So the fewer collisions, the lower the pressure. If you increase the volume, there's fewer collisions, lower pressure. So increasing the volume of the container will decrease the partial pressure of all species. If I decrease the volume of the system, that will increase the number of collisions and increase the partial pressures of all the species. So how does the system respond to this? If I increase the volume and I decrease the partial pressures of all the species, that pressure's going down. The system wants to shift to bring the pressures back up, right? So it's going to shift to create more gas particle collisions with the surface. So it's going to shift to either the right or left based on the total number of moles of gas phase species. So yeah, it's dependent on the specific chemical equation. So you look at the total, and this only affects gas phase species. You look on the left-hand side, the reactant side, add up all the total number of moles of gas phase species. Do the same with the product side. If those are equal, there'll be no effect, right? Shifting one way or the other wouldn't change the number of collisions and can't affect pressure. So there'd be no effect. But if one side has more moles than the other, then this will shift in response. So if I increase the volume of the system, decrease all the partial pressures, this will shift to the side with more total particles or moles of gas in response to bring the pressures back up, right? Depending on the equation. If you decrease the volume of the system, that will increase the partial pressures of all the species. Now the pressure is too high, so the equilibrium system is going to shift to the side with fewer total moles of gas-phase species to decrease the total number of gas particle collisions and decrease the pressure, bring the pressure back down. A little trickier one that you don't see very often is, what if I add an inert gas, right? I'm adding another gas. Now that gas is not part of the equilibrium equation, right? So it's not reacting with any species, whatever. It depends on whether the volume can change or not, really. If the volume of that container is constant, it's increasing the total pressure but not altering the partial pressure. So there's going to be no response for this particular system. But if we have a volume, if I add an inert gas and the volume expands in response, then you've got the type A problem, right? We have now increased the volume of the species, and it will shift exactly like things in part A. So let's do an example problem of this. A little harder to think about, but let's do it. All right, guys. So for this second type of disruption where we're changing the volume and thus the partial pressures, let's just do a simple one where we have monatomic oxygen gas reacting with diatomic oxygen gas to give us some ozone. Remember the triatomic or O3 oxygen? That's ozone. So if you want to have some fun in your board, go look up the ozone layer and ozone depletion. Fascinating, fascinating chemistry going on up there in the stratosphere. So let's say we change the volume of the system. It's at equilibrium, it's at its happy place, perfectly fine, but we increase the volume of the system. There's no way we could solve this problem until we figure out the total number of moles of gas phase species on both sides. Now, these are all gases. You wouldn't count it if it wasn't a gas. So on this side, on my reactant side, I have 2 moles of gas phase species. On the product side, I have 1 mole of gas phase species. Now you can do that in your head, or you can write it down. It's up to you. But a big common mistake that I find students do is if I give you an equilibrium system that has a solid or a liquid or something in there and gases, they count the moles of all species. You can't do that. Only gas phase species. So for this one, I have 2 moles total of gas phase species on the reactant side on the left, and 1 mole of gas phase species total on the product side on the right. Those are different, so a change in volume and a change thus in the partial pressures of species will have an impact on this. If those were the same on both sides, there'd be no effect on there. It'd be pretty boring. So let's say in A, if the volume is increased, what's going to happen when we increase the volume? The partial pressures decrease. Right? Boyle's law. So if I increase the volume, the partial pressures are going down. So Le Chatelier's principle says it's going to shift to bring pressure back up. So which way is this going to shift to increase pressure, i.e. increase the number of gas particle collisions with the surface? It's going to shift to the side with more particles of gas. So this would shift to the left, right? To bring the pressures back up, counteract the disturbance. Now let's like here, if the volume, obviously this is going to be the opposite, right? If that shifts left, this next one's going to shift right. If the volume is decreased, pressures go up, right? The partial pressure, more particle collisions. So the system goes, the pressures are too high, shift to bring them back down. So it's going to shift to the side with fewer moles of gas, which would be to the right. So the result would be it's producing fewer total moles of gas, fewer particles of gas, fewer collisions, brings those pressures back down. So not too bad when you think of it that way. So we got one more to do. We're done with this whole chapter. Woohoo! Let's look at temperature effects. Remember to review exothermic and endothermic reactions. All right, gang, to understand this last disruption or disturbance temperature changes, again, you have to know what exo and endothermic mean. And we're going to cheat or fudge a little bit, and we're going to think of heat as a product or reactant, right? Even though you're not really changing the concentration of the heat, we're going to think of it that way to make this easier. So remember, by definition, exo means to give off, therm is heat, so exothermic reactions give off heat. We're going to think of heat as a product in that type of situation, okay? So on the right-hand side, we're going to put heat as an actual species, a product species. If it's an endothermic, endo means to take in, so it's bringing in heat. For endothermic reactions, we're going to treat heat as a reactant. So we're actually going to put heat on the left-hand side as a reactant. And if we alter the temperature, we're going to count a temperature increase as an increase in heat and a temperature decrease as a decrease in heat. And if we know heat is a product, exothermic reactions, or a reactant, endothermic reactions, and we increase the temperature, we increase the heat, right? So if the temperature is increased, think of that as an increase in the concentration of heat. And based on the first type of disturbance, if you increase the concentration of something, it's going to shift away from it to counteract that disruption or disturbance. So if we increase the temperature, we're increasing the concentration of heat. This system will shift away from the heat. So if it's an exothermic reaction where heat's a product, it's going to shift to the left away from the heat. If it's an endothermic reaction and heat's a reactant, it's going to shift to the right away from the heat. So it depends if it's, you have to know if it's exo or endothermic to solve these problems. That must be stated to you, or they actually give you the enthalpy of the reaction, right? And vice versa, if the temperature is decreased, we're decreasing the concentration of heat, right? So if it's an exothermic reaction where heat's a product and we're decreasing the temperature and decreasing the heat, it's going to shift to the right towards it to replenish it. If we have an endothermic reaction where heat is a reactant and we decrease the temperature or heat, it's going to shift left towards it in order to bring it back up. So think of it like a concentration one. Let's do an example, and we're done with chapter 15. All right, let's polish this off. So let's say we have a reaction here. We have some diatomic nitrogen gas reacting with some diatomic hydrogen gas. to give us some ammonia gas. I think that's the Haber process. And they give us a heat of reaction or enthalpy of reaction of negative 91.8 kilojoules per mole. We have to think about what that is. So there's two ways. They'll either tell you it's exo or endothermic, or they'll give you the enthalpy of reaction, heat of reaction. If it's negative, that means heat's being released. So we can conclude from the information given that this is an exothermic reaction. So I'm going to write that in there. Right? Heat's being given off. A positive value would be endothermic and a negative value would be exothermic. So sometimes they add that little extra layer of thinking on a quiz or exam, but sometimes if we're in a good mood, your professor will tell you it's an exothermic reaction. The numerical value doesn't matter. All that matters is the sign, right? I don't care how big or small that number is. If it's exothermic, I'm going to treat heat as a product. So I'm literally going to go plus heat. I'm going to write heat as an actual product, which allows us to revert back to the first type of disturbance, changes in concentrations. If that was an endothermic reaction, I put heat as a reactant. So if the temperature is increased, picture this as a quiz or test. If the temperature is increased, I'm increasing the heat. If I increase the heat, it will shift away from it. If you're increasing the concentration of heat, it's going to shift away and shift left. It's a great way to control things in the laboratory environment. If you want to force an equilibrium system to shift left or right, you can alter the temperature of that system. Hey, we love to control things as chemists so we can make more goodies. Now, if the temperature was decreased in this scenario, we're decreasing the concentration of the heat. So in that scenario, if we're decreasing the concentration of heat by decreasing the temperature, it went down, so it's going to shift towards it to bring it back up. So this would shift to the right. Of course, the opposite of what we did in the first part here. Pretty straightforward. So practice Le Chatelier's principle. Work on your homeworks. Work on any kind of worksheets or other assignments that has been given to you, and practice it till you can do it in your sleep with your brain tied behind your back, and you'll kick some butt on the exams. That's what we're after. That's your tournament champion, right? Let's have at it, gang. You guys rock.